Okay, so let's get right into chapter 5 here. Z-scores, right? We're going to learn how to do Z-scores today. So here's some data from two students about texting behavior from our class, right? So student X says they send 30 texts per day according to our survey, and student Y says they send 200 texts per day according to our survey. So in order to interpret these numbers, what pieces of information might be helpful? Well, one thing that might be helpful is a measure of central tendency, right? Specifically, the mean, the median, or the mode. Let's just go with the mean here, right? So the mean number of texts sent in our class was 106. The remaining measures of central tendency data are located there underneath in terms of the median and the mode. So given the mean of 106, we might ask, well, does student X test very much? I don't know, tough to say. They seem to be fairly well below the mean. What about student Y? What 94 text messages per day, higher than the class mean? I don't know. Is it pretty extreme, or compared to the mean, is it relatively close? It's very difficult to say. Is sort of my point, just by looking at the individual scores comparing to the mean. So, what other piece of information might be helpful here? Well, maybe a measure of variability, right? In fact, probably the most useful measure might be the standard deviation, because as we've learned before in previous chapter, in chapter 4, when we were talking about variability, standard deviation is in the same units as the mean. So if we knew what the standard deviation is, we get a sense of how far each individual score is from the mean. And here the standard deviation for our data was 195 text messages. So remember, standard deviation is the typical deviation from the mean. So on average, the number of text messages people send is about 195 text messages away from the mean of 106, right? That's 195 is one standard deviation. So given the standard deviation, we can see that even though 30 is much less than the mean, it isn't exactly extreme because it's within one standard deviation, right? It's within the typical distance of the mean, if you will. Same thing with student Y. 200 messages is still within one standard deviation of the mean. Now, one thing I want to point out, though, it might seem pretty obvious looking at these data, but this will really make it obvious. This data itself, all of it, comes from really a terribly non-normal distribution. Here's a histogram of our data. So here we have a positive skewed data. And as we can see by looking at it, most people are within the 0 to 300 range. Most people are. A little handful of observations sort of above that, really only 3. But it looks like there's one person who texted a heck of a lot more, right? That person claimed to have sent over 1,000 text messages a day. So you can see, here's the standard deviation and measures of central tendency here again. You can see the influence of the outlier on these data is quite extreme. So how would this change if we were to remove that outlier? And again, I'm doing this a bit arbitrarily. I would never do this with real data collected from an actual experiment. We have procedures which we use that are non-biased, that say whether or not we can remove an extreme observation from our analysis. Here, though, for the sake of our explanation, I'm just going to go ahead and remove that one person who claims to send over 1,000 text messages a day. And you can now see what happens to our standard deviation and our mean, right? Our standard deviation drops to 70.81, I think this says, and our mean drops to just a hair below 70, right? We can round it up to 70. And now, if we ask the question whether or not the person who sends 30 text messages or 200 text messages is extreme, I think it's much easier to answer that question. 30, we still say no. 30 is still within one standard deviation of the mean. But now 200 text messages, well, that's quite extreme, right? Because that's 3 standard deviations above the mean, right? So I start with the mean of 70. If I continue to add 70.81 to this mean of, again, rounding it to 70, by the time I finally get to 200, I'm already 3 standard deviations above the mean. So that's quite an extreme score. And this slide is sort of for fun to see how the class compares to the national average of 18 to 24-year-olds, which is typically college age. So they report sending 128 messages a day. All right. So our data is actually a bit lower than that, but we of course haven't done a actual analysis here, but you get the idea. So yeah, getting back on track to sort of shift over to the textbook. The textbook uses the example of test scores, and the point I'm getting at is, before we looked at these data on text messages, and we said, well, okay, a person who sends 30 text messages is within one standard deviation of the mean. That's not very extreme. Somebody who sends 200 is 3 standard deviations above the mean. We would consider that an extreme score. But we're still speaking a bit vaguely here, right? And so does this, right? Let's imagine you get a 76 on the exam, right? The exam is coming up. Is that good or is it bad? Well, we all have our individual standards, but it also depends on the class, right? In classes, 76 is a really good score. In others, it might be about average or even relatively low. So just as it was with the text message example, knowing the mean, knowing the standard deviation, that helps us put this score into perspective, right? So with a mean of 70 and a standard deviation of 3, 76 is a fantastic score, right? It's at the head of the class, right? But let's say we had more variability in our data, right? We had a standard deviation of 12. Well, if you look at here, this is the data plotted out. A raw score of 76 is roughly half a standard deviation above the mean, so it's above average, but not by much. So the point is, in order to interpret any particular score, it's helpful to understand where that score lies in the distribution, right? How does that score compare to the mean? And also importantly, the variability, right? The standard deviation of the distribution also comes into play, right? Because it's another sort of descriptive statistic that tells us something about the sort of shape and overall performance within that data set. In one useful way to compare a raw score and sort of its performance within the overall distribution of scores is to make those comparisons in terms of standard deviations, right? So the first exam is coming up, right? So imagine you get an 81 out of 100 points. And so your raw score, right? The original unchanged score is a direct result of the measurement. That raw score is 81 on the exam. Now we can use the mean and the standard deviation of the distribution, right? For everybody that took the exam, right? And we can transform your raw score into what we call a z-score, So it's a standardized score, right? And it has two functions: to describe location and to allow for comparison. So first of all, rather than just knowing that the raw score on the exam is 81, right? That's what you got. We're going to have a precise understanding of how that raw score compares to everybody else who took the exam. So we're going to know the location, right, of your score relative to all the other scores in the distribution, right? And we're going to talk about it in terms of how many standard deviations your raw score was above or below the mean. The second part about z-scores is that it allows us to compare scores across different distributions, particularly scores that might be on different scales in particular. So imagine your first exam score is 81 out of 100, and your scores over the homework assignments, let's say we take the sort of first batch sort of out of 90 points, you got an 82 out of 90 points. You might be asking, well, where are you performing better? Well, it's difficult to compare these raw scores directly, right? We can't say, well, you got an 82 on the homework and an 81 on the exam, so you're doing better on the homework. And the reason why we can't just compare them that way, at least not in any meaningful way. I mean, obviously we can compare them that way, but we can do it in a bit more meaningful way. And the reason why we do this is because these scores are on different scales, right? Your exam is out of 100. The sum of all of the homework points leading up to the exam is 90, right? So they're on different scales. We need to standardize them, and we can standardize them. When we do that, it puts them on the same scale. We can talk about them in terms of how different they are in terms of standard deviation units away from the mean. Now, one way we could do this is by converting each of these to a percent, right? But that doesn't let you know how you're doing compared to, say, other students, right? Which is something else that we use z-scores for, right? We might be interested in your performance on both the exams and the homework compared to other students' performance on the exams and the homework. So what we can do is convert each raw score into a z-score. And this will show us how your relative performance on the exam compares to your relative performance on the homework. And we can also judge how your performance compares to everyone else's performance in the same distribution for that specific assignment. So I'm going to start off the lecture by talking a bit more about the first function, right? The idea of using z-scores to find location for a raw score in a distribution. And then I'll come back to this idea of comparisons. So a couple of things to make sure that you understand about z-scores before we get into the mathematics of this, which are very, very simple today. The standardization process gives us the relative position of each score in the distribution. So you need to be aware of these two things. First of all, a score's sign, and secondly, a score's value. So the z-score sign, right, whether there's a plus or a minus in front of the z-score, it indicates whether a score is above or below the mean, right? So a score that is plus something is above the mean. A score that is minus is below the mean. And this is as good as time as any to really reinforce this idea that you need to include the plus and minus sign whenever you compute a z-score, right? So a lot of times it's almost a force of habit. If we calculate a z-score and it turns out to be, plus 2.31, right? A lot of times we forget to put the plus because we just assume, well, since there's no negative value, it's automatically a positive number. But remember, in order to get full points, you have to put the plus or minus sign. So don't forget to do that correctly. The second thing about a z-score is its value, right? The actual number. The numeric value tells us how far above or below the z-score is from the mean, right? So it indicates the distance, right, between the raw score and the mean, but it indicates its distance in terms of standard deviation units. And you'd always report a z-score out to two decimal places. Even if you compute a z-score and it's 1, you would report that as being plus 1.00. So here's an example. If a z-score is negative 1.00, what that means is that the raw score is one standard deviation less than the mean, right? So let's say in real units of the original data, let's say the standard deviation was 6, right? It doesn't matter what it is. It could be exam points, right? So the standard deviation equals 6 exam points. What this means, what this negative 1.00 means, is that whatever the raw score was, it doesn't matter what it is, but whatever it was, it corresponds to a z-score of negative 1.00. And in the original raw data, a z-score of negative 1.00 means that the raw score was 6 points less than the mean. So here when we standardize the scores as z-scores, we're talking about how far the raw score was away from the mean, right? Either above or below it. Okay. So remember, on the exam, you're going to need to be able to interpret z-scores by saying, whether that person has scored higher and lower than the mean, and by how far. So let's say you take your exam, and I convert everybody's scores into z-scores, and you had a z-score of 3.00. Okay, well, how far are you away from the mean? You're 3 standard deviations away from the mean. 3 standard deviations away from the mean. Are you above or are you below the mean? Well, this plus sign indicates that you're above the mean. So you're 3 standard deviations above the mean. And would you say you're much better or slightly better than the typical student? Well, we should know that 3 standard deviations above the mean is quite excellent, right? We would only expect, if you remember the curves that we talked about using the normal distribution, you'd only expect around 2% of all people in the class to perform that well, right? So you're much better if your z-score is plus 3.00. You're much better than the typical student who took the exam, if indeed that's what you end up with, which I hope you do. And it's sort of a bonus question here. Let's say we figured out the z-score for the mean exam score. What would that z-score be? Well, it should be 0, right? Because Remember, z-scores tell you how many standard deviations away from the mean a raw score is. Well, the mean itself should be 0 standard deviations away, right? So a z-score of 0 is the equivalent of whatever the mean is of the raw score from the original distribution that it came from. This slide might make things a little bit more intuitive, right? So a z-score of 0 equals the mean, right? Which is the mean of the raw score. And imagine, if this is a distribution. Let's pretend that we computed z-scores for all of the raw scores in a normal distribution. All right, well, whatever the mean was, it would be a z-score of 0, right? A z-score of plus 1.00, like here, for example, 1.00 above the mean would indicate somebody's 1 standard deviation above the mean. A z-score of negative 2.00, that indicates somebody is 2 standard deviations below the mean. And it doesn't matter what the mean is or what the standard deviation is for the raw scores, because remember, each raw score has been converted into a z-score, right? It's been converted into a standardized distribution using the original raw score as well as the mean and the standard deviation of the raw data. All right, so let's get into the formulas. They're not terribly difficult. To compute a z-score, what we do is we take the raw score, subtract the mean from that, and whatever that deviation is, we're going to divide that by the population standard deviation. So that's how we would compute a z-score. Trivially easy. Also, if we know the z-score as well as the population mean and standard deviation, we can sort of work backwards and find out what the original raw score is. And we do that by starting with the mean and adding to that whatever our z-score is times the population standard deviation. And we're going to be utilizing both of these formulas quite a bit. Okay, so here's our data from our stress scores, right? We had a mean of 71.6 and a standard deviation of 18.4. And I'm treating our stress scores for the sake of this example as if they were population data, okay? So what I want you to do, right, you have your formulas from the previous slide right here. So make sure you have them down in your notes, right? What I want you to do is compute the z-score. This was our lowest score in our distribution. It was 40. So I want you to compute the z-score for the person who reported a predicted stress score of 50. And remember, whenever you're doing this, particularly on the homework, in order to get full points, you want to show the formula, show your work, and then what I want you to do is plot out a normal curve, right? I want you to plot where the mean is on that normal curve. And then I want you to plot where that z-score is relative to the normal curve. Because you're going to have to do all that in order to get full points on your homework. So go ahead, pause the video, and compute the z-score, plot out where that score is on a normal curve. And when you come back, I'll show you how I would have done it. Okay, great. So remember, we start off by stating what our formula is. And also I should tell you, the homework might ask you to compute multiple z-scores. Let's say the very first problem on the homework asks you to compute a z-score. All you need to do is show your formula for that first one. If problem 2 also asks you to compute a z-score, there's no need to show your formula again. As long as you show it once, the first time that you have to compute a z-score in the homework, then that's fine, right? But don't forget, if the homework asks you to compute a raw score, you're going to want to show that formula as well. So you'll always show the formula at least once and you're fine, right? So that's our formula. And here's the math, right? I'm going to take that raw score of 50, right, which is my x value, subtract our mean out of that, which is what I'm doing there. And whatever that is, divide that by our standard deviation of 18.4. So I get, in my numerator, 50 minus 71.6 is minus 21.6. If I divide that by 18.4, I get a z-score of negative 1.17. And then, like I said, I want to go ahead and plot that on a normal curve. And here I have the benefit of finding one on the internet. You just have to sketch one out and just do the best you can. I'm not going to sit there with a ruler measuring out how symmetrical your normal curve looks. Just get it close. That's fine. Just make sure to label where the mean is, and remember that the mean equals 0. And again, fortunately, I have one to scale. So negative 1.17 standard deviations, which is slightly past negative 1.00, right? Again, when you're sketching these out, just get close to it, right? You know, as long as you plotted it somewhere in this area, that's fine. If you ended up plotting it over here where the plus values are, well, obviously that would be a mistake, right? But, you know, as long as you get it in the neighborhood, you're fine. And so, you know, this is all you have to do, right? These steps here, show the formula, show your work, and plot where your z-score is on a normal curve. That's all you have to do in order to get full points on the homework questions. Okay. So I went ahead so remember I told you can, let me go backwards here, that you can use this formula to find the z-score, right? But I also told you if you know the mean, z-score, and standard deviation, you can find the original raw score. So I went ahead and took the liberty of computing the z-score for the median value in our stress level data. And it turned out that z-score was negative 0.22, right? So the median for this data set for stress scores had a z-score of negative 0.22. What I want you to do, right, is use this formula, right? Use this formula to find what the original raw score was. So what's the raw score associated with a z-score of negative 0.22 in this particular data set? Again, remember, show the formula, show your work, and you'd plot the location. In this case, not the z-score. I should change that. I should change that to say the raw score on a normal distribution, right? So go ahead and pause the video and try and figure out what the raw score was. And don't forget to plot where that raw score is on the distribution. And when you come back, I'll show you how I did it. Okay, so here's our formula again, right? X, the raw score, equals the population mean plus the z-score times the population standard deviation. So we're trying to figure out what X is. So we start with our population mean of 71.6, and we're going to add that to the product of negative 0.22 times 18.4. And so, as you see here, I'm breaking it up into steps. You could enter this into your calculator all as one shot if you wanted to. As long as you at least wrote this part down, that's enough showing your work as far as for an easy problem like this. But whatever you feel comfortable with, note here that what I'm doing is the order of operations, right? It says to do everything in parentheses first. And so when I multiply negative 0.22 times 18.4, I get negative 4.05. So 71.6 plus negative 4.05 gives me a value of 67.55. So my median in this place, I've got a little bit of a rounding difference, but the actual median of our data turned out to be 67.5. So that's close enough. But don't forget, I want to plot that, but here I want to plot the raw score, right? So remember, the mean for our data, raw data, was 71.6. If I then plot 67.5, it's somewhere around there, right? And so again, that's close enough, but don't get confused. If it's asking you to find a raw score, and you then have to make plot a normal distribution and plot where that raw score is on that distribution, be sure that you use the raw score values and not the z-score values. It should be self-evident as you're doing it, right? Because, you know, you'd be sort of hard-pressed to plot a z-score here because you'd probably start sort of scratching your head and going, well, why am I doing that when I just computed the raw score? It sort of makes more common sense. It's more logical that I would want to plot the mean raw score and the raw score that I just computed, right? So hopefully that makes sense to you. So everything that we've been talking about can also apply to samples. I mean, in fact, it's a bit artificial, right? Because in reality, we've been working with sample data so far in this whole lecture, and we've just been pretending it's population data. But, you know, if you were running z-scores, you know, on a sample, everything's still the same, but instead of using Greek letters, you're just using letters from the English alphabet, right? So X minus the sample mean divided by the sample standard deviation, and vice versa, right? The sample mean plus the z-score times the sample standard deviation, right? So the only thing that changes is the notation. The equations are exactly the same. Okay. And I should go back. This isn't trivial. We're going to get to a point where we're using samples exclusively for the most part. I mean, we haven't got there yet. We're still a couple chapters away. So, you know, while this idea isn't really applicable to your homework, it's something that we're going to be revisiting in a few chapters. Okay. Again, now is the point in time where I'd ask you if you have any questions. As always, if you have questions, you can certainly post them online. Although I'm starting to realize that the course website doesn't do a very good job of telling me when somebody responds to things like announcements or post questions. So you might want to just email me to be safe. Or if you have access to a tutor, the tutor can help give you a little bit more insight into these procedures. Okay. Let's just jump into an example here. Let's do something a little bit more difficult than just finding z-scores for a single raw score. Here, I want to dive into the idea of comparison, right? So I can compare performance for people across different distributions. And this is very similar to one of the questions that's going to be on the homework. I think might relate to the SAT or something like that, or the GRE. I don't recall exactly. So here's our scenario. The day after performing a novel motor task in a lab, a non-athlete and skilled athlete perform an additional task, right? So now a different task, to see how well the previous task generalized to their performance on the second task, right? We study this in motor research, right? We teach you how to do some sort of intricate motor performance, and then we give you a completely different task to do, and we see if the things that you learned from the previous task help you on the second task. So anyway, here we're measuring performance on the second task here. The non-athlete had a score of 63. So this is one person's score, right? One non-athlete, not a bunch, but one non-athlete had a score of 63, and a skilled athlete had a score of 59. Now here, these are the distributions that these individual raw scores came from. So the non-athlete got a 63, but if we take the mean of all the non-athletes, we get a mean of 60 and a standard deviation of 6. Whereas the skilled athlete got a score of 59, but if we look at their distribution that they came from, that distribution had a mean of 55 and a standard deviation of 4. And what we're asking here is who showed better improvement on the second task. Now remember, we're interested in the generalizability between the two tasks in relation to athletic skill. And we can't just simply compare the raw score of 63 for the non-athlete to the raw score of 59 for the athlete, because those scores come from two totally different distributions. You might say, well, look, the non-athlete got 63, the athlete got 59. Clearly, the non-athlete did better. In terms of raw score, that might be true. But we have to take into consideration how well or poorly the distribution that they came from did, right? The mean for all non-athletes in the second task was 60 with a standard deviation of 6, whereas the mean for all skilled athletes is 55 with a standard deviation of 4. To meaningfully be able to compare these, what we need to do is standardize both of these raw scores, right? So we need to convert each of these raw scores into z-scores, so that we can compare the individual z-scores, which will allow us to take into consideration their performance, right? How well they did relative to how well everybody else in their group did. So what you need to do is convert both of these scores to z-scores, right? Both of these scores to z-scores using their respective distribution, plot them, and that should tell you something about really who did better given how well they performed relative to their distribution. So go ahead and what I want you to do is just simply pause the video, right? Pause the video, compute the z-scores for both of these raw scores, plot them, and then write down who you think actually did better. And when you come back, I'll show you. And don't worry if it's that last part is a little challenging, right? You're like, well, gee, I'm not really sure how to interpret this. That's okay. I'll help you interpret it when we come back. All I want you to do is try, right? Do the best you can to try. Okay. So, like I said, what I want to do is compute the z-scores for the non-athlete and the athlete. And again, this part can be a little tricky. Here's our formula. Remember that the non-athlete came from a distribution with a mean of 60 and a standard deviation of 6, right? So when we compute their z-scores, that's the mean and standard deviation we want to use. We don't want to make the mistake for the non-athlete using the distribution that the athlete came from, because that would be wrong. We want to use the distribution, right, the mean and standard deviation that the non-athlete score of 63 came from. And so when we do that, we plug in their raw score of 63 minus the mean. So 3 divided by 6 is going to give us a z-score of plus 0.50. And don't forget to report it out to 2 places. It would be a mistake to just say it was 0.5. You have to say plus 0.50. Z-scores need to be reported out to 2 decimal places. And don't forget the plus or minus sign in front of it. Now we compute the z-score for the athlete, right? So they had a raw score of 59, but their distribution was different, right? Their distribution had a mean of 55 with a standard deviation of 4. So 59, right? Their raw score minus the mean, 55 is 4. So 4 divided by 4 is going to give us a z-score of plus 1.00. So I go ahead and I plot them now, right? I plot the z-score and I label where they came from. It can be a bit difficult to be organized here. I've tried to do the best I can. I think it's not a bad job, right? Here's the mean. The non-athlete had a z-score of plus 0.500. So they were halfway, half a standard deviation above the mean. Whereas the athlete had a z-score of plus 1.00. They were a full standard deviation above the mean. So who showed better improvement on the second task? Well, hopefully your answer was the skilled athlete, right? And here's my explanation. Even though their overall score, raw score, was lower than the non-athlete, given the performance of their distribution, the skilled athlete actually showed the greatest improvement between the 2 tasks, right? They showed the greatest improvement relative to their distribution than the non-athlete on the same task. So hopefully that made sense to you, right? If it didn't, you might want to go back and watch the video. Again, watch that portion of the video. Make sure you're doing the readings from the textbook, and hopefully that'll make sense. The point is, once we standardize the scores, right, then we can meaningfully compare them, right? We've converted them both to z-scores. And that gives us a z-score that indicates their performance relative to their distribution. At this point, raw scores don't matter anymore. And again, like I said, you can't compare one raw score from one distribution to another single raw score from a different distribution because they both had different means and different standard deviations. The only way you can meaningfully compare them is to convert them both to z-scores, because that takes into account the mean and standard deviation that their original raw score came from. And then you can see actually it tells a quite different story. Really, the non-athlete was only half a standard deviation better than the mean compared to all the other non-athletes, whereas the skilled athlete was one whole standard deviation better than all the other skilled athletes, right? Above the mean and the standard deviation for their distribution. So who showed the greatest improvement? The athlete actually did. That particular athlete was better compared to the non-athlete. Okay. So I want to talk a little conceptually here, and this ties into one of the questions on the homework about measuring saliva collection, right? It sort of revisits Pavlov's experiments. And so I'll say here that I want you to sort of encode into memory. The z-scores have something to say about where someone's score falls on a distribution, and they reflect how many standard deviations a raw score was from the mean, right? So essentially they're asking, how many points did people differ from their group mean? Okay. So let's go think about our previous distribution of scores here. In the distribution for the non-athletes, right, that had a mean of 60 and a standard deviation of 6, let's say we had somebody, her name was Jenny, and she had a z-score of plus 1.37. Now, if you had to explain what that meant for somebody who knew nothing about statistics, how might you explain this to them, right? If you wanted to explain how well Jenny did compared to everybody else, you couldn't really say, well, Jenny had a z-score of 1.37. Like, try telling that to your mom or your dad, right? Assuming they maybe never took statistics, or they took statistics a long, long time ago and they've forgotten all about it. You say, yeah, Jenny was 1.37, had a z-score of 1.37. They're going to be like, thanks for that information. It's utterly useless. It doesn't mean anything to me. So how would we explain this to somebody that might not know anything about statistics? Okay, well, remember our formula here that we learned, that if we had the population mean, the z-score, and the population standard deviation, we could plug all of that into this formula, and it would give us the raw score, right? So we know our mean is 60, right? Our standard deviation is 6, and our z-score is 1.37. So if we take 60 plus 6 times 1.37, it gives us a raw score of 68. So somebody, Jenny in this case, who had a z-score of 1.37, actually has a raw score of 68. So now things become a little bit easier when we're trying to really tell somebody what it means to have a z-score of 1.37 above the mean, right? What we're saying in the real world is that Jenny had a score of 68. Right? And that score of 68 was 8 points better than the average non-athlete. So see, we can take something as complicated as a z-score, right? Use that as well as the population mean and standard deviation to find the original raw score. And we can talk about our data in terms of the original units that the raw score was measured in, right? So look, Jenny did this motor task. She got a 68 on it, which was 8 points better than what the average person did, who in her group that performed on the same task. So as you can see, it's just sort of, there are ways we can make it easier to explain these sort of differences in terms of standard deviations and differences from means. We can do that in a way that makes it easier for people to understand. And I don't want you to think that this is a trivial thing. It's quite important. Not only is it important for the homework, because you got to do it on the homework, but for those of you that might be interested in a career in science, even when we're talking to other scientists, right? Even when we're giving presentations to colleagues at professional society conferences, you were always trying to figure out a way to explain our data in the most simple, accessible way possible. It doesn't pay to use a lot of jargon, because just because you understand some jargon, there may be people in the room that don't do the exact type of research that you do, but may have an interest in it because it relates in some meaningful way that maybe you're not aware of to maybe questions that they're asking. And the last thing you want to do is assume that everybody understands what you're saying. The last thing you want to do is talk over everybody's heads, right? You want to explain your data, even to fellow professionals, even to fellow researchers in the most easiest and precise terms as possible. So there's a value in being able to take complicated things like z-scores and means and standard deviations and breaking that all down in a way that allows you to explain your data to anybody. Okay, again, this is the point where I would ask if you have any questions, but we're not able to do that. So let's just move on. Okay. So we've been talking about location. We've been talking a little bit about comparison. And I want to shift slightly, still staying in the realm of comparison, but we're going to make it a little bit more complicated here, right? So now, I'm going to move on to discuss not just a single standardized score, but I want you to imagine what might happen if I computed a z-score for every single score in a distribution, right? So a standardized distribution is a distribution where all the raw scores have been transformed into new values in order to create a predetermined mean and a standard deviation, right? That's what we're going to do with these data. It's a little complicated, but fortunately you can always sort of go back and listen to things if I'm going a little too fast or you don't quite understand what it is I'm saying. But a general example of this is just an entire distribution of z-scores, right? If every x value, right, if every raw score in a distribution was transformed into a z-score, right, then we would have a distribution of z-scores. And that distribution of z-scores would have some very specific properties that I want to talk about, okay? The first one is that it's going to maintain the shape of whatever the shape of the raw score distribution was, right? So the individual locations of z-scores compared to raw scores in a distribution, they don't change, right? If you started off, if you were converting all the raw scores in a distribution into z-scores, and the original shape of that raw score distribution was negatively skewed, then the distribution of the z-scores is also going to be negatively skewed. So your shape for your distribution of z-scores is going to end up being the shape of whatever the original distribution was for your raw scores, right? Now, the mean, right, of all z-scores is going to be 0, and that's going to be equivalent to whatever the mean of your raw score was, right? So remember, our raw score mean of stress scores was, I think, 71.6. If we convert that 71.6 to a z-score, the z-score would be 0, right? So the mean of the raw scores is the same thing as the mean of your z-scores, and the z-score value would be 0. The standard deviation, right? The standard deviation of all z-scores is simply going to be 1. So a distribution of z-scores is an example of a standardized distribution. All the scores are transformed so that there's a set mean and a set standard deviation. And all z-score distributions have a mean of 0 and a standard deviation of 1, and they maintain the shape of whatever the shape was of the original raw distribution. So why are we doing all this, right? It seems like an overly complicated process, right? Like, so why are you converting all the raw scores into z-scores? Okay. The reason why, believe it or not, z-scores are easy to work with in raw scores, right? They still have decimal places. They still have negative numbers potentially, which can be confusing for people, right? Especially once we get sort of outside the classroom in the research setting. So to deal with this problem, what we can do is we can use our z distribution that we compute to create a simpler standardized distribution built off our z-scores, right? So sometimes it's useful to transform a set of raw scores into a completely different standard distribution with a new mean and a new standard deviation. SAT does this. As of right now, and this could change because the SAT people change the nature of their test from time to time, but the math test is 58 questions. And the verbal score that you get is actually generated from 2 sections that combine for a maximum of 96 points. But somehow on both tests, you end up with a score that is on the lowest end of 200 to the highest end of 800. How is that the case? Again, there was only 58 questions on the math exam, but your score is somewhere between 200 and 800. And both of the verbal tests that they use to compute your verbal score is out of a max of 96 points, but that also has a score of 200 to 800. How do they do that? Well, what they do is they create a new standardized distribution. So here's what SAT does. They transform all your original raw scores, right? So the original raw scores that are either within 58 or 96 points, right? Because they're coming from 2 distributions. They transform your original raw scores into z-scores based on the mean and standard deviation of the year you took the SAT or whatever test version that they used, right? So in other words, they take they find the mean of everybody's math score that year, and they find the mean of everybody's verbal score that year, and they take everybody's individual raw score for the math exam using that mean and standard deviation, and then again, everybody's individual raw score on the verbal test using the mean and standard deviation of the verbal test that year, and they convert every individual score into z-scores. So that's what's happening in step 1. That's their first step. They take the mean and standard deviation for that test for that year, and they compute z-scores for every single raw score for every single person who took that test that year. Okay? So they get a bunch of z-scores for everybody. They then transform those z-scores into new raw scores based on a mean and standard deviation that they created, right? Which happens to be a mean of 500 and a standard deviation of 100. So here they're using the z formula to figure out everybody's z-score. And here they're using the formula that allows you to find the raw score if you know the z-score, the mean, and the standard deviation. So let's do an example. Again, it's a little tough, so you can always sort of wind back for help, right? But let's do an example. So here I've got an example from the verbal test from 2016. And remember, they're going to create a new mean, a new distribution rather, with a mean of 500 and 100. But we're not there yet, right? We're just still dealing with the raw scores from the verbal test. So the raw SAT score for everybody who took the verbal test in 2016 was 85 with a standard deviation of 4. And we're picking one person out of that distribution. We'll call them person A. They got a raw score of 88. What I want you to do is compute their new standardized score on the new SAT distribution. So let me be really specific here. That means you're going to have to compute a z-score for this raw score of 88, right? Then you're going to have to take that z-score and the new mean and the new standard deviation for the new distribution that SAT has created, and you're going to have to figure out what the new standardized score is given this z-score and given this distribution. So again, don't worry if you struggle with this, right? It's a little bit complicated. It's a little bit confusing. You know, when we're doing this in person, I have the benefit of being able to go through the individual steps with everybody, right? But, you know, I want you to go ahead and pause the video and give it a shot on your own. And then when you come back, I'll show you how to do it. Don't worry. Don't be too hard on yourself. Okay, so remember, I said the first thing you need to do is compute a z-score, right, based on this distribution, right? Because we have a raw score of 88. That came out of a distribution with a mean of 85 and a standard deviation of 4, right? So if we can compute the z-score, right, take the raw score minus the mean and divide that by 4, right, we get a z-score of plus 0.75. Now remember, we have to now figure out where that z-score will fit into this new distribution that has a mean of 500 and a standard deviation of 500. So we can use the z-score, use this new mean that SAT created, and use this new standard deviation that SAT created in order to compute what a z-score of plus 0.75 would be coming from this distribution, what that z-score would be for the new distribution with a mean of 500 and a standard deviation of 100. And when we compute that, we see that the raw score is 575. Now, we're going to write that down. We're going to sort of put that aside for now. We're going to come back to it, right? But what we did, to just sort of reiterate, to go back, is say, okay, here's the mean and the standard deviation for all the verbal scores in 2016. And here's one person's raw score. We're going to compute their z-score. We're going to see that they did 0.75 standard deviations better than everybody else who took the raw score. But remember, these are not the scores that SAT reports. They create a new mean and a new standard deviation, and they take the z-score that you get out of this, and they put it into this, to put it into this equation, and they figure out, okay, this is what your actual score is on the SAT. Okay? All right. So now we've got SAT scores in 2012. This is a different year. And in that year, it was a mean of 73 with a standard deviation of 5.7. And now we have another raw score from somebody who took the SAT in that year, and they got an 88. Now, you might recall, that's exactly the raw score that person A got. But remember that they took it in 2016, and the distribution that they came out of had a different mean and standard deviation, right? So now what we want to do is find their z-score, right, for their distribution, right, and then convert that z-score again into the new SAT distribution with a mean of 500 and a standard deviation of 100. And what we want to ask ourselves is who did better, person A or person B? Remember, they got the same raw score. We're going to ask how well they did in comparison to the new distribution of SAT scores that we're using. So go ahead again, find the z-score first, right? Then use that z-score and the new mean and the new standard deviation to figure out the actual SAT score. Plot both the new SAT score for person A that we figured out at the previous step, right, which was 575. Also plot person B's score and try and answer the question, who did better, person A or person B? So go ahead and pause the video. See if you get it. It's the same steps as we did for person A. So hopefully it should be a little bit easier. Okay, so person B also had a raw score of 88, but they came from a different distribution that had a mean of 73 and a standard deviation of 5.7. So if we take 88 minus 73, that's going to give us 15. If we divide that by the standard deviation of 5.7, we get a z-score plus 2.63. Now, knowing that z-score, we can find the new raw value, right, by inserting that into an equation that uses the mean and the standard deviation. But remember, we're using those values from our new distribution, the one that SAT arbitrarily created. That has a mean of 500 and a standard deviation of 100. So let's do what's in parentheses first. 2.63 times 100 is quite easy. It's just 263. We add that to the mean of this new distribution, which is 500, and we end up getting a score, right, performance for SAT for this person that got an 88 in 2012 of 763. So let's go ahead and plot them, right? Person A had a SAT score of 575. Person B had an SAT score of 763. So who did better? Well, in this case, person B did. Remember, they got the same exact raw score, right? They both got an 88, right? It's just the distribution that they came from is different. And that matters, right? Maybe SAT had a bit of a different version for the test that year. Maybe that was affecting scores. Who knows? But the bottom line is those scores came from different distributions. So in order to compare them, first we need to standardize them. And SAT goes a step forward. SAT goes, you know what? To make this even easier, rather than just talking about just telling a student, oh, you did this many z-scores above the mean. What we're going to do is take that z-score and we're going to put it into that formula that helps us find a new raw score. But we're going to set the mean for this new distribution at 500 with a standard deviation of 100. This way, it doesn't matter what year you took it. It doesn't matter what version you took it. SAT can map the performance of every single person that ever took the SAT, and you can get every single person a score that they understand, somewhere between 200 and 800. And you can do this conceivably until the end of time, right? SAT can do this for as long as they're administering this test, right? They can use this methodology of finding everybody's z-score for their original raw score, and then getting a new score off a new standardized distribution that they created and saying, that's your SAT score. Kind of complicated, but incredibly useful, right? It's an incredibly useful thing. It is just another tool, even though the math might, be a two-step process and seem a little bit confusing. It's still a relatively easy way for everybody to understand how they did, in relation to how somebody else did. The last thing I want to talk about here before ending for the day is this idea of grading on the curve. It works a lot like the way the SAT stuff works. It's probably not what you think. A lot of students seem to think that when a professor grades on the curve, what they do is they take whatever the best score was, say the best score somebody got on an exam was 92, and they treat it as if that was 100%, right? And then they adjust everybody else's scores accordingly. But that's not actually grading on the curve, right? That's actually changing everybody's score by a constant. And whatever that constant is, it's the difference between the best score and a perfect score, right? Gradient on the curve actually means fitting everybody's scores into a standardized distribution. So what I'm talking about here is let's pretend this is the grades at the end of the year, right? And the mean for everybody at the end of the year, the mean grade was 80, right? So a B minus with a standard deviation of 12.4. Well, let's say you did a bit better than that, right? You got an 85, which is a solid B, right? That's your final grade for the end of the year. Well, let's say I wanted to fit everything under a curve. What I'm going to do is create a new distribution where I say sort of the middle point is 70 with a standard deviation of 10, right? Well, what would your 85 actually be under this new distribution? The way we're going to figure out is the same way that we figured out the SAT scores, right? First, we're going to find the z-score for this raw score of 85, and we're going to use the mean of 80 and the standard deviation of 12.4. Once we have that, we're going to find a new x value, a new raw score, and we're going to use whatever the z-score is here, but now we're going to use the mean and the standard deviation for this new distribution, right? And so what we're asking for is, what would your grade be under this new standardized distribution? You can pause the video and figure it out if you want to for yourself, or I'll just sort of do it with you. So it's up to you. All right, so here we start off by figuring out the z-score. So we had a raw score of 85, which was your final score for the class, minus 80, which was the class mean. So that's going to give us a difference of 5 divided by the standard deviation for the class of 12.4. And that gives you a z-score of plus 0.40. So pretty good, right? Almost a half standard deviation above the mean, right? So you did better than the rest of the class. But remember, I'm grading on the curve, right? So I'm going to take that z-score and I'm going to fit it into our equation that allows us to find a raw score for our new distribution, right, with a mean of 70 and a standard deviation of 10. So if I do everything in parentheses, 0.40 times 10 is going to give us 4. So the mean of 70 plus 4 gives us a raw score of 74. Yeah, that's not good, right? That's sort of sad, because if I didn't grade on the curve, you would have got a B. But if I grade on the curve and force all of the scores to fit into a new distribution with a mean of 70 and a standard deviation of 10, all of a sudden your B turns into a C. I probably don't think you would like that very much, right? So be mindful in the future. If you ever ask professors would you grade on the curve? Be careful what you wish for. It's fine if the variance is a little bit lower, right? If this standard deviation was less than 12.4, well, your 85 is going to be more standard deviations above the mean, right? Here, it's only 0.4 standard deviations above the mean. If this value, you can practice by doing it yourself. Let's say the standard deviation was, 3 or something like that. If you divide 5 by 3, you're going to get a much higher z-score, right? And then if you were to plug that into this equation using this new mean that I've set and this new standard deviation, well, then you're going to perform better. So when grading on the curve, if the overall variability of the class is high, it makes it really, really difficult to get a good score. It means that your original raw score has to be even more exceptional in order for it to be, more than one standard deviation above the mean. So be careful what you wish for. Typically, you don't want to ask professors to grade on the curve. You should typically be content to, it's probably a better strategy to just be happy with the grade that you get. Okay, fantastic. Here's some practice problems from the back of the book. I think these practice problems can help you on the exam, help you better understand the subject matter. So now we've gotten through 5 chapters, right? 5 chapters. Chapters 1 through 5. We've gotten through everything that's going to be on the first exam. So it's likely my next lecture depends on, look at the syllabus to sort of be sure about the scheduled dates. But I'll lecture on chapter 6, and this will give you a little bit of time for me to grade homeworks and give you a little bit more time for you to study before the exam occurs. But again, just check the syllabus. Be sure that you're aware of all the dates of when things are supposed to happen. But exam 1 is only going to be on things covered on chapters 1 through 5. So when we continue on to the next lecture, we're going to be covering stuff that will not be on exam 1, but will be on exam 2. So that's all I have for today. So good luck. Again, if you have any questions, please ask.